Okay, looks like it's going. Okay, so here's where we were last time. We were talking about. Before I dive in, a couple of quick things, logistical matters. The hurricane messed up my plans for getting grading done this weekend. We were out of power at my house for a long time. So my revised estimate of getting the grading done is later this week. I have to have it done by Friday. Right, I have to have midterm grades submitted, right? So I'm predicting some late nights in my future, and I hope to get. There's an optimistic chance I might get it done Wednesday. If not, then definitely Thursday. So that's the situation there. Okay. One other thing. So office hours, as y'all recall, is set up to be right after this class, as it turns out. And due to a mistake on my part, there's kind of a double booking for the room. You know, my outer part of my office that I use for office hours. So it's fine. We're going to hold office hours. I just might have to move it. And I've already contacted the other party, and I think I have a solution in place. But anyway. Heads up, if I'm not in there, look for a sign on the outer door there as to where I've moved to. Okay. So here's where we were last time. We were talking about vector fields, right? And that vector fields can represent a lot of different things, and among them, it can represent fluids. And the way that a vector field can represent fluids varies. But one way is for the vector field to tell the velocity of the fluid. Okay, and so we went through a calculation as a result of that, and what we found was that there was this thing called flux, computed by that formula right there, that gives us the answer to how much fluid per unit time is passing through a given surface. All right, here's the weird thing. That same expression ended up being the answer to a different question also. So with the first question, reminder, if the vector field represents velocity, then we compute volume per unit time. But what we found, or what y'all are going to find when you go through the analogous calculation, again, I think that's a good exercise, and I want y'all to take a shot at this yourselves. If the vector field represents density times velocity, then it tells you mass per unit time. I didn't really quite hit that right, did I? Let me circle there we go. Mass per unit time. So the details are a separate point. The main thing I want to get to is that this expression, vector field dot normal times area, this expression, again, worthy of a name, we call it flux. We use the capital Greek letter phi to represent it. This is an object of significant interest, right? And in the sense that, well, it tells you something natural if your vector field is one way. It tells you a different something natural if your vector field is a different thing, right? Key point, though, it's natural. Okay. So, what I want to do now is entertain a more complicated question, which is, what if you have a different kind of a fluid flow? And in particular, there are some kind of fluid flows where it's really hard to define what the velocity is. And for example, let's suppose you have a light source right here. And if you think about it, lights create photons. They're constantly shooting out photons. Photons are little teeny tiny little things that kind of flow, right? It's like there's a fluid emanating out of this light source. It's one way to think about what light is. It's a fluid. But here's the other thing. Maybe you also have a light source here. And so a reasonable question could be asked, okay, well, what's the velocity of the fluid flow at this point over here on the right? Well, some of the photons are going that way from the orange bulb, and some of the photons are going this way from the blue bulb. So what is the velocity? What should the vector field be at this point, right? What are we going to do about that point? We got a problem. There is no single velocity representing whatever you want to call it, velocity or density times velocity, representing what's happening at that point. There's a bunch of things happening. The photons are going every which way. Everybody see the problem? So we have a solution to this. I think this is a nice idea. And that is to take this formula that we have from the previous page. Right? I'm going to think in terms of masses, not volumes, because it's a little bit more, general, a little bit more relatable, I think. And instead of thinking of it as, hey, if I know the velocity, or if I know the vector field, then I can compute the mass per unit time. Let's instead pose, what if I were to know mass per unit time through all different possible surfaces? Couldn't I just use that to figure out what the vector field ought to be? And that's what the answer is going to be. If you have a circumstance where there's a fluid flowing, right, but you can't directly define the vector field, then we say, well, if I have some way to get my hands on this, if I can, whether it be empirically with measurements, right, or whether it be by some other argument, if I can figure out mass per unit time through surfaces, there's going to be a vector field that makes this formula work. That's the vector field that we're going to use to represent the fluid flow. Okay. Now, a little quick point of order. If you go back to how we defined flux, you look at this picture here. We've only defined flux for little pieces of area that are small and flat. That's the only thing that I've done any definition for. But I'm going to say, and we're going to make this much more precise later in the course. But I'm going to say you can do similarly for other nice surfaces, and I'm going to make an argument about a non-flat surface in a minute here. But the big idea is it's still, you want to look at little pieces of surface and think about the extent to which the vector field is going through, anyway, so we're gonna extend this naturally and believably, and I just have to confess in advance. Okay, all right. So here is an example of how we can use the above idea. Let's suppose we have here a uniform ball of glowing gas. What a strange consideration, but not all that weird if you really think about it. Some gases glow, right? Neon, for example, and they don't just glow on the surface; they glow throughout the entire interior of the like everywhere inside where the gas is. It's all glowing pretty much the same, and or at least as we're assuming here. Okay, so all of these little particles of gas are emitting photons, and I want to try to figure out what is the vector field that represents the flow of the photons. So the first suggestion I'm going to make is that if you're interested in a surface like this one, right? So there's a little spherical surface. And if you're interested in the flux through that surface, the first big point is any gas that's outside of the surface shouldn't contribute to the flux. Now that seems wrong, because surely look at that. I mean, this glowing gas right here is emitting photons, and it's clearly hitting the surface. So how could I say that it doesn't contribute to the flux? Well, here's the big point, and let me zoom in so I can see this better. This photon goes in, and it enters the sphere there, but then a fraction of a second later, it keeps going, and it leaves the surface there. So it goes in there, it goes out on the other side. One of those is going one way through the surface, and then the other is going the other way through the surface. And in total, those are opposites, those are canceling, right? Going the other way through the surface is, it's like it goes back out. And so it's like, as far as flux through that surface is concerned, it's a zero. It doesn't count. That makes sense? There's just as much light going out of the surface as there is going in to the surface. Okay. So this is a huge first point that we don't have to think about the gas that's on the outside. So all I really have to think about is the gas that's on the inside. And here's the good news about the gas on the inside. The gas on the inside, whatever gas you have there, some point on the inside, how much of the light that it emits goes out through the surface? All of it. 100%. It doesn't matter where within on the inside or how bright it is. All the photons go out. Right? So what this tells us then is if you're interested in the flux through this surface, all you really need to know is how much gas is there inside of it. And the gas, just based on the amount of gas that you have, well, then all of its photons flow through, and it's those photons that define the flux. And so this is our first formula that we have here. I have the rate of flow of photons through that spherical surface. All it depends on is how much gas is there. And I'm going to call that the volume. Now, of course, density matters, and then how brightly does the gas glow also matters. That's all. Do keep in mind this is a uniform ball, and so all of that stuff is constants, and so therefore taken care of by the fact that I have this K. I don't know what K is, but there's some constant there. Okay, so how are we doing on the first big point? Does everybody believe that the flux through this surface is proportional to the volume? Everybody happy? All right. So here's the next point I'm going to make about this question, and that is I'm going to suggest that this should be a radial vector field. This vector, keep in mind, we're looking for a vector field that represents the flow of the photons. Of course, there's photons going every which way all over the place because there's sources of photons everywhere throughout this whole ball of glowing gas. But altogether, the vector field should be radial, and it's just a symmetry argument. This is a uniform ball. Balls are symmetric. And so the vector field representing it kind of has to be symmetric. I mean, what's the vector field going to be at this point? Is it going to be that way? No, it just can't be, right? If it were off axis, if there were an asymmetry to this vector field, that would suggest that it was brighter over here than it is over here. And it's not. It's a uniform ball. So I claim the vector field has to be radial and therefore pointed outward like that. Does that seem plausible? Okay. All right. And radial vector fields have the nice feature that they point in the same direction as these normal vectors that I'm going to draw here like this, specifically normal to a centered sphere like that. So if you look at a centered sphere, its normal vectors are radial. The vector field, we just agreed, also radial. So these vectors point in the same direction. And therefore the dot product, F dot n, that we know we're going to need in our flux calculation, well, that's an easy calculation. The angle between these two vectors we're dotting, the angle is 0. Furthermore, one of them is a unit vector. And so altogether, F dot n is just the magnitude of the vector field. Now, I'm giving you all kind of patchwork little pieces of ideas, and it's not clear yet how they fit together. But they're going to come together just momentarily here. Okay. All right, so here's where it all comes together. Here is our, what you might call, wrong mode. Here's what you might call our definition of the vector field. The vector field needs to be that which makes this formula tell us how much in this case, photons per unit time are passing through any given surface. And keep in mind we are considering this surface right here. So on the one hand, I previously argued, hit the wrong button. Previously argued that the amount of flux has to be proportional to the volume, because after all, the volume on the outside doesn't matter. Any gas that's on the outside, light flows in and then out, net zero. And gas that's on the inside, all of its photons flow through. So a nice simple formula there for the left side of our definition equation. F dot n, recall, we just argued there, has to be the magnitude of F. So starting with, again, our definition of the vector field, this blue equation, we know how to compute the left side, we know how to compute the right side. And now I can kind of bring it all together. And let's see here, the area of the sphere, of course, we know is 4 pi r squared. Old geometry formula for computing area. Let's see here, the volume of the sphere. That volume on the inside there. Another old formula from high school geometry. Right, 4/3 pi r cubed. And so altogether, we know these things have to be the same, and that allows us to solve for the magnitude of the vector field. Magnitude of the vector field is proportional to the radius. As it turns out, a constant there, k/3 ends up being the constant, how it just happened to turn out. And if you know the magnitude of the vector field, and if you know that it's radial, that means you know the direction of the vector field. That uniquely defines the vector field. There is only one vector field that's radial, and it has magnitude given by this formula, and you can confirm for yourself that this is it. It's the x vector field times this constant k/3. So weird little calculation, but we start with a very difficult question that we don't really immediately know how to get our hands on, because there's photons flying every which way as originating from various different pieces of gas inside of this thing, all over the place. Altogether, though, this vector field here represents the flow of all of those photons. Okay. Yes.
What would X look like?
Yeah, well, so this is the vector field where your field vector is the same as your position vector. And so this looks like, you may recall, we drew a picture of something similar to that back. Here it is. The field vector is the same as the position vector, and it gives this kind of outward radial sort of a look.
Okay.
Is that familiar?
Yes.
Yeah. Good. Okay. So one last thing I need to say about flows of fluids. This is in the book, and it's just kind of an observation that has to get made. We're not going to be fleshing this out too much, because it turns into a differential equations problem, and we don't really have that under our belts yet. But the idea is, suppose you have a vector field, and let's, for the moment, suppose that vector field represents the velocity of the fluid flow. So you've got some sort of a fluid, maybe it's air, water, whatever, and you've got a vector field describing the velocity of how that is flowing around. If you were to drop a particle into the fluid, the idea, this is something that doesn't, gravity doesn't influence it, it just kind of goes where the fluid goes. And if you want to know, as this particle follows the current, well, it's going to trace out some path. What is that path? How do I get my hands on finding what the path is that this particle follows? Right. So, for example, in here, you could imagine if let's suppose that because I'm standing here talking and I'm blowing air that way, and maybe let's say that's making the air kind of slowly circulate like this, right? Well, we could speculate that if I were to drop a floating little particle right here, that it would kind of go that way, and then it would sort of turn around, and then it would kind of make sort of, you would expect sort of circular paths, right? So we call that a flow line. That's a line representing how particles would be pushed by this fluid that's flowing as it is. Okay, now, algebraically, how do we represent that? Well, it's just a matter of kind of writing down what we just said, but writing it down with equations. The velocity of the particle, right? So how do I describe the velocity of a particle? Well, it's the derivative of the parametric curve defining the position of the particle. The velocity of the particle is the same as the velocity of the fluid. And keep in mind, the velocity of the fluid is what's pushing the particle, so of course the particle should have the same velocity as the fluid. But don't forget further that the velocity of the fluid is the vector field. Okay, that was our assumption, is that, in this case, how we're representing that velocity is with this vector field. And so altogether, then we have a differential equation that says the vector field evaluated at the position of the particle gives you the velocity of the particle, and this is what's called a system of differential equations, and that'll be covered in Math 353. I'm 99% sure it's not covered in Math 218, so I don't think y'all have seen that before. Used to be covered in the old Math 216, but not 218. But anyway, so this is a differential equation we don't have the tools for, but anyway, it can be solved. It's just technique, it's just methods, and you'll see it later. But the most important thing to understand is what a flow line is. A flow line is just the path followed by a particle that's dropped into the fluid. It's the big idea. Everybody good? All right. Okay, so just a quick example, and I'm skipping over the actual solving of the system, but if you just notice, this path here is a flow line for that vector field. And now how do I know this? I know this because if I take this path, if I look at what the value of the vector field is at a point on that path, I will find that it is the same as the velocity of the path, namely the derivative of the path. And you can just compute that directly. Right? Easy calculations on both sides of the equation there. Okay. So again, this is a pulled it out of a hat kind of a situation. I did not solve for this. I just manufactured an example of what a flow line is, not how to find it. Okay. Okay, how are we doing? All right. Okay, so a last comment before I go on to the next thing, and that is that I've given you two metaphors for vector fields. We talked about vector fields as forces, right? So I wrote down some vector fields that represent gravitational fields and electric fields. And you can talk about other kinds of forces that might be applied in various circumstances. There are lots of forces in the world, right? And so you can use vector fields to represent forces, and it's a natural application of vector fields. But there's this totally independent idea that you can use vector fields to represent fluids as well, right? And again, makes total sense. It's the perfect tool for describing how fluids flow, because that's what a fluid flow is wherever the fluid is, it's got to be going a certain way, etc. So the point I want to make sure you understand here is you need to understand both of these. So it's not the case that you can just kind of pick one, the one that you like the best, the one that makes the most sense to you at the moment, and that can be the way you think about all vector field questions in the course. It just doesn't work. There are certain kinds of calculations that we're going to be doing, certain kinds of interpretations we're going to be making of vector fields, where you have to think about the vector field as representing forces. It does not make sense if you take the fluid point of view. And there are other applications where you have to think of the vector field as representing fluids, and it will not make sense if you think about it from a point of view of forces. So please make sure to digest both of these applications, as will be very important as we go on. Okay. All right. So this last section in Chapter 3 is kind of a weird one. I am going to do it here in Chapter 3 because the book does, and again, I feel like I can only sort of digress so much. I can only deviate so much from the way the book does things. But a lot of what's in Section 3.4 here is really pretty premature. So think of this as kind of foreshadowing. What they're doing here is introducing you to some tools that are going to end up being really important in chapters 6 and 7. Mostly chapter 7, right? So this is pretty premature. Tools that we're going to use in chapter 7. And the problem is, I'm all for introducing ideas earlier and letting students digest them. The problem is, I'm going to be making just completely unjustified assertions as to what these things are that I'm about to tell you about, and why, or what is the context, and what's the how should I think about this, and what makes this all work is stuff that we just don't have the tools to do yet. And so this is, like I say, I think this is premature, but we're going to do it anyway because the book does. And so my apologies, and adjust your expectations accordingly. What I'm about to tell you should not, don't think of it as something that should follow and that you should understand every bit of. Think of it as, I'm just going to tell you I'm going to make some assertions, and you're just going to have to kind of trust me on them. So anyway, that's what we got here. So y'all know this formula here, right? Gradient. And we've seen some nice facts about the gradient, ways to interpret it, how it connects to various different things. Okay. So I want to interpret this as being, rather than a single notation representing one thing, I want to interpret this instead as sort of two things coming together. I want to think of it as the del represents things I'm going to do, and that the f represents the function I'm going to do it to. Right? So think of this thing on the left, this green, this upside down triangle, as being, it's like it's a vector that's made up of not things, but of actions, you might say. And so, so we're gonna make this definition. We call this the del operator. Importantly, we're not gonna call it the gradient, because gradient is what you get when you apply that to a function in this specific way. We're gonna do other things with the del operator that are not the gradient, and so we want to distinguish between del that can be applied to a function to give you the gradient, as opposed to the gradient itself. So del is kind of a more general construction. Yeah.
Would it be wrong to call something the del of f?
Yeah, you could say del f. Yeah, if you want to say del f, that yeah, I think that's fine. Yeah, I mean, it just in the culture, my experience is that people usually say gradient. But if you're in the middle of an equation and you just you don't want to waste the syllables, then you say, yeah, people know what you're talking about. Yeah, totally. Okay, so I want to get one thing out of the way, and that is a confession that this I'm writing it like it's a vector, but is it really? I mean, I thought a vector was supposed to have elements that were numbers. Is partial with respect to x, is that a number? Or, what is that thing, right? It's not really a number. So this is an awkward thing. It's not exactly a vector. It's what I'm going to call a symbolic vector. And it's kind of like when we were talking about cross products. Right? And remember, we defined cross products with a certain formula that we thought of as a symbolic determinant. Algebraically, you kind of treat it like you're taking a determinant, even though, it technically doesn't really quite fit the bill, but that if you do, everything goes through fine and it's not a problem. So, same deal here. We're going to treat this like it's a vector, even though it's not, and it's going to turn out that everything's going to be fine. So, this is you might call this an abuse of notation, and I wouldn't argue against that. But it's very common. It's very convenient. So we're gonna go with it as the rest of the world does. Okay. All right. So the first definition I'm going to make for you, and again, pulling this out of a hat. Do not look for intuition on why this is true. We do not have the tools yet at all to understand why the things that I'm about to claim are true. We'll start with a definition, something called the divergence of a vector field. Again, this will be a big deal in Chapter 7. A little bit in Chapter 6, actually, but mostly in Chapter 7. And the divergence of a vector field is what you get when you dot. Again, as if del were a vector, when you dot the del vector, which is made up of these partials, with a vector field which has these components, right? And interpreting the dot product in the way that it would seem sensible, right? You've got these this green vector, you've got this purple vector dot. You think this is what dot ought to mean, and this is the definition of divergence. So, coming out of nowhere, no intuition for why we'd be interested in such a thing. And, again, a little uncomfortable with the fact that we're doing a dot product which we would expect to do to two vectors involving one thing that's not really a vector. And, again, we're going to let that slide, and we're going to pretend that it's a vector, and, again, it's just a convenience. Okay. Alrighty. So, reminder, we don't have the tools to make sense out of this yet. So again, my apologies. So I'm going to make a complete baseless assertion, and that is that what this thing represents, trust me now, right? And we'll make sense out of this later. But the book wants us to have a preview of what's coming. What divergence represents is the amount that a fluid is flowing away, kind of flowing outward away from the whatever location it is that you're looking at. So it represents an outward flow of fluid. Let me show you an example. So let's look at this vector field right here. And again, this is the vector field where the field vector is the position vector. And recall we talked about that previously. So this is what that looks like, our old vector field friend. And let's compute the divergence using the formula above. And the formula above is that right there. It's the sum of the partials. And now keep in mind, we're going to take the field components, x, y, and z. That's what f is, right? And then we're going to do the del dot. So we're going to take the x, y, and z partials of those first, second, and third coordinates, respectively, add them up, because after all, that's what a dot product is, right? And you punch this up, these partial derivatives end up being convenient, because, well, again, not a coincidence that I chose this vector field. I wanted a nice, easy one to start off with, right? So I've arranged it to where this would work out nicely, and the divergence here ends up being 3, which you'll notice is positive. And so now let's return to the interpretation. The claim that I made was that divergence is supposed to represent this outward flow away from where you're interested in. Well, we're looking at the point 0. We're looking at the origin here. Right? Arbitrarily, not that it matters. But at the origin there, I think this tracks, right? I think this is as claimed. This says we have a positive amount of divergence, a positive amount that fluid is flowing away from the origin, and sure enough, yes, clearly it is. There it is. You can see the fluid's flowing away from the origin. Okay, now this doesn't prove anything. It tracks. It's consistent, at least, with the claim. But this is an example of what we claim divergence means. Yeah.
So does it actually give the amount of stuff? That is.
I'm being deliberately sloppy with my language. To make this precise, it involves, again, the tools that we don't yet have at our disposal. So you got me, and I'm going to clean it all up later. Yes.
And then, so vicinity, is that an arbitrary vicinity? And we'll talk about it later.
We got to keep it sloppy here, because there are very clear and crisp answers to your questions, and they involve chapters 6 and 7 tools that we just don't have. Yeah.
So if you evaluated it at the variable vector xyz itself instead of at 0,
mm-hmm.
would you still get 3?
Yeah, you do. So that's a great question. So what if we're not looking at 0? What if we were looking at let's say some arbitrary point x here? I picked 0 just because I wanted to it serves my purposes of being, it's clearly flowing away from there better if it's the origin. If it's not, if it's, let's say here, a point like that, it's a little harder to see. I claim it is still the case that the fluid is in net. The fluid is flowing away from this point. Roughly speaking, because there's less fluid flowing in because the field lines are shorter there, and there's more fluid flowing out because the field lines are longer there, right? So in the net altogether, there's still, it's a little harder to make sense out of, but it's still, I hope, a little bit believable that we would say the fluid is flowing outward away from there. But so that's why I didn't want to look at in general. You're right, it does work in general. It's just harder to make sense out of. But at the origin, I think it's pretty clear, and so that's why I chose it. Yeah. Right. Okay. All right. Now, physically, what does this mean? And this is an awkward discussion because it could mean different things. And so the physical interpretation we make of when the divergence is positive, and we get this kind of outward flow like this, what's physically happening? And there's two possibilities. Correction, there's two, you might say, extremes of possibilities, and the truth could be any combination or any sort of thing in between these two possibilities. So one possibility, I think these are both pretty relatable actually, one possibility is that this represents the flow of a gas of some sort, and here's the thing, if the gas is flowing outward away from some point, there's less gas over time. Right, because the fluid's flowing out. I mean, the gas is leaving, right? So if you have a certain amount of gas and some of it just decides to go away, then there's less left over. So this could be representing a decreasing density of the gas. That's one possible physical interpretation. Does that make sense to everybody? Here's the thing, though. It doesn't have to. That's possible. Instead, that what we have here is called a source of fluid. Right? And this is also entirely reasonable. Easiest example, I think, to see would be imagine that this is a light bulb. Right? If there's a light bulb here, photons flying outward everywhere. Just like any other light bulb. Is the density of photons decreasing? No, not at all. It's not that photons were previously here and are leaving. It's that photons are being created and then leaving. And so there's no change in photon density at all. So these are kind of, like I say, sort of opposite extremes of each other. Either could be the case. Or, and again, it could be sort of a combination of these. And that's a little harder to talk about, but it could be either. Okay. All right. Again, all of this is going to get fleshed out more substantially in Chapter 7. All right. Now here's another example. Got a vector field here. I'm going to leave it as an exercise for y'all to convince yourselves that this is what that vector field looks like. Right. Notice that the horizontal component is 0. And thus all the flow lines are horizontal. Right? And then notice that the x component, the left-right component, is larger when y is higher. And that's why you get longer field lines over there. And then as you go down, the field lines get shorter. And then as you go where y is negative, the field lines are actually going to the left. Okay, so I guess I just did that for you. Okay. You can compute the divergence for this vector field. Simple calculation, you get 0. And I think this kind of tracks as well. This is hopefully intuitively satisfying because kind of like we were talking about before with the glowing gas. Remember, and I was computed the vector field for the glowing. The first big example we did today. If you have some region, wherever it might happen to be, it doesn't even really matter where, but wherever you might happen to be, there's just as much fluid going in as there is going out. So in the net, the fluid's not really flowing out in net. It's flowing just as much in. So it's just kind of a push, right? Kind of a wash. So again, consistent with divergence being 0. Okay. Alrighty. All right, next tool that I'm going to show you that we do not have the tools yet to be able to make sense out of. And so again, this is a highly premature, and the book does this, by the way, I'm sure, to kind of, get the idea in your head, let it start kind of settling, maybe kind of, getting comfortable with thinking in these terms, perhaps, is their point of view. But I emphasize, do not try to derive any of the results I'm about to show you. We do not have the tools yet. Okay, that said, here's another definition. It's this thing called curl. And the curl is defined by this formula. And this is another symbolic formula, right? It's a determinant of what looks like a matrix, but it isn't, because the stuff in there isn't what's supposed to be inside of a matrix. Right? So another abusive notation, but very convenient, very useful, very broadly used. And so heads up that you are going to see this, even though it's a little bit sketchy. It's a very common and very convenient notation. Okay, so again, notice that it is making use of the del operator. Again, we're treating the del operator as if it's a vector. We are doing the cross product of the del operator with the vector field whose curl we want to take. And cross products, of course, as you know, cross products are computed as this particular symbolic determinant. Okay, so arbitrary definition, pulling it out of thin air, no context, no tools for making sense out of it. But there it is. This is called the curl of a vector field. All right, so what am I going to baselessly claim this means? Here it is. The curl of a vector field represents the what I'm going to say, how much and around what axis is the fluid circulating? To what extent do we have this kind of a thing? To what extent is the fluid kind of creating... Oh, gosh, and I have to be... Again, I'm doing a lot of deliberate hand-waving and humming and hawing because there's a proper way to say this. It involves tools that we don't have yet. So, have to be hand-wavy. But curl represents how much, roughly speaking, the fluid is kind of flowing around, kind of like a tornado or, like a hurricane, to be timely, that sort of thing. Okay, does everybody see my baseless assertion? Yes.
What is CCW?
Oh, yeah, thank you. In the same sense that if we're going to talk about how much fluid is flowing through a surface, there has to be a sense of which one is the positive direction and which one is the negative direction. Likewise, if I'm going to say that if I've got fluid flowing around an axis, then there's a difference between it going that way around the axis versus it going that way around the axis, right? And so I say here counterclockwise, just to indicate which is what we consider the positive direction around the axis.
And is that always the case, or can we define our axis?
No, this is a standard convention, and counterclockwise was chosen long enough ago that it's we don't have any. It's deeply embedded in the culture at this point. Yeah. It was initially an arbitrary choice. Yeah. Okay, let me show you an example so you can get a feel for what I'm talking about here. Here is a vector field. Now, we've not drawn this exact vector field, but we drew something very similar to this. We drew the two-dimensional version of this vector field, where f of x comma y was negative y comma x, and we argued about right angles and stuff, and that this is a kind of a flowing, making little circular flows, right, like this. The difference here is that this is now a three-dimensional vector field, and this is not just happening in the plane; it's happening in all of space. And then the other difference is that there's no vertical component, and so in some sense, it's like all of these counterclockwise flows are just kind of being copied and repeated as you go up. like that. Is that cool? All right, so let's compute the curl of this thing. You compute the you compute the curl. Here's the formula. Punch it out. You get this. Now, keep in mind that's telling us two things. That is telling us both how much circulation there is and around what axis. Right. So 0, 0, 2. Well, that is a vertical vector like this. The 2 is a measure. We're not going to talk about the units or how to be precise about exactly what 2 means here, but 2 is a representation of, in some sense, how intense the tornado is. Whether this is a really strong one or a really gentle one, right? And the direction here, the fact that this is pointing straight up, is the indication that the flow is around that vertical axis. As opposed to, let's face it, there are some flows that would be maybe around a horizontal axis. And that's not what it is because, again, the direction of the curl indicates the direction of the axis that it's rotating around. Is that cool? Now, again, this doesn't prove squat. Right? This is just an example that's consistent with my baseless claim. One example to show kind of what the claim is saying. It doesn't prove anything, and we do have to fill in those blanks when we get later on into chapter 7, somewhat chapter 6 as well. Okay. Yeah. Mm-hmm.
The 2, does it correspond to the angular velocity?
Something like that. Yeah, I have to be sloppy and vague at this point because it corresponds to something that can be made precise, and we will make it more precise later on. I am still actually, even when we get to chapters 6 and 7, not going to bring in precise, like units. Units are meters per second or whatever the units are going to be is kind of a choice for a specific context that we're just not going to deal with in this class, and that's something that you can fill in your engineering classes and such. Yeah, roughly speaking, the 2 is an indication of what the total amount of swirliness, if you will, of the field is. Yeah. Okay. All right, now by contrast, here's another vector field. You can persuade yourself it looks something like this. You can compute the curl, you'll get 0, suggesting that this fluid flow, that there's no circulation. And I think that's highly consistent. You look at the picture, you don't see any swirls or anything like that here, right? In fact, you can see all the flow lines are straight lines, and that would seem to suggest that there's nothing swirling. Asterisk. I'm going to come back and correct that. I'm making a deliberately false suggestion there, and I'm going to fix it in a couple seconds. But straight lines, again, doesn't look like swirling at all. Yes?
How do you read the curl? On the previous example, it was 0, 0, 2. So how do you interpret that?
How do you interpret the curl being 0?
No, it's for the previous example.
Oh, yeah. So the curl is this vector. That's a vector that has a direction and a magnitude.
Yeah.
That direction defines an axis.
Yeah.
And the claim then is that this is the axis that, at least at, the point where we're evaluating, right? In the vicinity of that point, the vector field is kind of swirling around that axis.
Okay.
Does that make sense? Yeah. And then if you want to know what's happening at some other point, you'd have to evaluate the curl wherever that point is. Yeah. All right. Let me give you a different way to think about curl. It's kind of a slight refinement of what we just talked about. Rather than thinking about how any piece of the fluid is flowing, think instead now, just a different way to think about it. Suppose I had a floating, I'm going to say a balloon, right? And it's got just, how when you have a helium balloon and they go up to the ceiling, and then like 3 or 4 days later they start to kind of come down a little bit, and they sort of get just that perfect buoyancy to where they effectively weigh 0, and they just kind of float aimlessly around the room, right? So perfectly weighted helium balloons. What I want to think of this as. And what would happen if we had a perfectly weighted helium balloon like this, And if it were sitting in an airflow per this picture here, and I appeal to your physical intuition, the fact that the air is doing this would make the balloon itself start to spin, wouldn't it? Does that make sense? I mean, a little bit at least. It depends on how much the air can kind of get a hold of the rubber, but you would think that the balloon would start kind of spinning around. Okay. There's a different way to think about it. What would happen to such a helium balloon in this case? Well, it wouldn't spin at all. It might start moving this way, but it's not going to spin because in some sense it's being pushed, you might say, in opposite directions on both sides. It's being pushed what you might call counterclockwise from this side, and it's being pushed what you might call clockwise from this side. And so no spinning, consistent with the curl being 0. Okay, different way of thinking about curl. And that relates to the next example. It is tempting to look at this vector field and think, hey, I see nothing but straight lines. Those flow lines are straight lines. I don't see any circulation. I don't see any swirling at all. But that's just not the right way to think about it. The right way to think about it is with the balloons. And I pose, if you put a balloon right there, and look at what's happening to this balloon. Well, the balloon's being pushed on the one side. It's being pushed kind of, that way, which you might call clockwise. On the other side, it's being pushed seemingly the opposite way, but it's the opposite way on the opposite side, so still clockwise. So wouldn't you expect that if this were the airflow, even though the flow lines are all straight lines, wouldn't you expect this balloon to start spinning clockwise? And curl picks that up. That's the cool thing. Curl is this, and you might say, as seen from down here, where the head of the curl vector is, if you were looking up at it, it would look like it's spinning counterclockwise. So, so heads up, the right way to think about curl is not about what the flow lines are doing. It's about what the balloon would do. Is the balloon kind of spinning and twisting around or not? Oh, and I'm out of time. Okay, all right, well. Okay, so be it. We will pick up here on Wednesday. Y'all have a good day. See you later. And again, quick reminder, if you're coming to office hours, if there's someone in there, then we'll figure it out. Okay, see you later.